Move into a new era of learning with Alma Mater.
How are you, everyone? Today we are going to look at binary coded decimals, and I'm going to just jump into giving the definition of BCD, which is the binary coded decimal. Alright, so in computing and in some electronic systems, we come across a situation where binary numbers are grouped to represent just one digit. A group of binary numbers or a group of ones and zeros will be representing a single digit. When we look at the way calculators, for example, in some old computers, the way they used to work, they had this small location for each digit, and that is where binary coded decimals were being applied. They are still being applied even nowadays. This may be a little difficult to understand from the definition which I have just given or from the explanation which I have given, but let me use an example to show how it works. Let's say I have my digital watch and it shows me the time 0, 7, 4, 5, like that. We don't want to represent or to call this number 745 because it is not. Each digit there is not related to the next digit in some way. It's not really related to the next digit. So when we are representing these digits, the 0, the 7, the 4, and the 5, we represent them each digit in a single register. Let me also give another example which contrasts this situation. For example, if we have 745, which is a number in base 10, this number can actually fit in a single register, and you can actually see how it increments from 45, from 5 to 4 to 7. These are units, these are tens, and these are hundreds. That's why we call it 745. But 745 has no such relationship between the digits. Now the calculator, let's use an example of a calculator. It looks at these numbers in this way. The 5, or the digit which is going to be in this position, is stored in this register. The digit which is going to come in this position is stored in this register. The digit for this position is stored in this register. And the digit for that position is stored in this register. So to represent 4 digits which are shown over there, we need 4 registers. And since a register stands for a single place, it means we can only put a number from 0 up to 9 in a particular register. We don't want a clock or a digital watch that is going to have something like 10 in place of 5 there. It will not work out because our time would end up looking like maybe 0, 7, 4, 10, and there is no time that looks like that. So each register or each position should have a single digit. Each register is carrying a single digit. That is the binary coded decimal format. Alright, we have a number of ways of allocating memory to these digits. We have the unpacked format where we have an 8-bit register holding one digit, and we have a packed format where we have a 4-bit digit holding 4-bit register holding 1 bit. Okay, Let's look at 5, for example. This 5, how is it going to be represented in an unpacked format? We are going to have an 8-bit register like this. 1, 2, 3, 4, 5, 6, 7, 8. All right. Now we know that 5 is 1, 0, 1, 0. 1, 0, 1, 0, 1, that is 5. These other 4 bits are going to be zeros. In an unpacked situation, we have an 8-bit register, which is a 1-byte register holding a single digit. It's obvious, knowing that we must have numbers from 0 to 9, it's obvious that the most significant nibble is going to be holding zeros, and the actual number is going to be in the least significant nibble. In other words, you will always have a situation where this will be zeros, and this is actually where your number is going to be. This one as well, let's look at 4. 4 is going to be stored in an 8-bit register as well. 1, 2, 3, 4, 5, 6, 7, 8. All right. And we know that 4 is 0, 0, 1, 0. That's right? Yes. Then the more significant nibble is going to be zeros as well. The same applies for a number like 7 here. All right. Okay, I'm not going to do all the numbers, but that is the unpacked format. Each numeral is encoded into 1 byte, with the most significant nibble always being 0 and the least significant nibble, so this would be the MSN, most significant nibble. This will be the LSN, least significant nibble, being the one which carries the number. This method, if you look at it, the fact that the most significant nibble is always going to be zeros means we are wasting resources. We are wasting this component, this register. We would rather use a register which is 4-bit, because a 4-bit will always be carrying the number. Every bit will be holding or contributing to holding the number. So that is the idea behind the packed method, the method of using a register, a 4-bit register, to hold each numeral. So each numeral will be encoded into a nibble. That is the packed method. Maybe as an example, let me do this to show the packed method. It's going to be easy. I'll just delete the other nibble. So in the packed, we have a situation like this one. We only allocate 4 bits to a digit. All right. So what would be the applications of the BCD method? We see a lot of use in calculators. It used to be used a lot in digital computers, the computers which used to just display maybe 1 up to 9, those funny cornered numbers or those funny cornered digits like what you see in digital watches. That is one of the most important uses of BCD. And in representing currency, BCD comes into play as well. You may have come across maybe banners which look like this. Let's say the number of days before a match or hours before a match. Let me say hours before a match. It would be a digital banner then that banner would be holding something like this. And so if you can see the way I was trying to show, you would see that this is 878 hours. This is 8, this is 7, this is 8. Now the register which is holding this 8, let me use the pegged system because at least I don't want to be writing all over the place. The register which is holding this 8, or the value which is going to be in this box, is 4 bits in size. That is the first thing, and it can only hold a number from 0 to 9. If you try to put a number like 1100, which is 8 plus 4, 12, it means you are trying to force a 12 to fit in this box. The display will not work because just by the sheer nature of the LCD that we are using, or whatever technology we are using to display that number, we will not be able to fit 2 digits in that box. Therefore, BCD allows us to put from 0 to 9 only. The same applies to this one and this one. So whenever you look at a register that is holding a digit for BCD, that register should have a digit which is between 0 and 9. If you see that the binary value of the decimal that may come out of that register is more than 9, like 10 for example, it means there is an error. It can be an overflow error, or the CPU has failed to detect that error. We are going to look at what kind of an error it is, but the methods which are used to check for those errors, we are not going to study them. They are not part of this lesson scope or even our syllabus scope. All right, now with BCD it's pretty straightforward. Let me give 5 examples. Okay, not 5, that was ambitious. Let me give you 2 examples and then go on to one of the contentious issues with this BCD thing. All right, so let's say I have $5.50. How is this value going to be represented in my computer's registers or in my electronic device registers? Okay, so each digit is going to have a register that is 4 bits. This is going to be repetitive and repetitive. All right, then we have that dot there. That dot does not move. It's not even going to be considered in this work that we are doing. We're not going to consider that comma there, and even that $sign, we are not going to consider it for now. We'll look at those things when we look at Unicode and stuff. So whatever digit is going to come here stays in this register. Whatever digit is going to come here stays in this register, and whatever digit is going to come here stays in this register. For that particular number, we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1. In other words, this is the BCD representation of $5.50, or 5,50, or 550. All right, if I have a watch that is telling me I am 8 hours 40 minutes. Okay, if I have a watch that is saying 8:40, it means that watch has a register that is holding a digit for this place, and it has another register that is holding a digit for this place, and another register that is holding a digit for this place. These registers, depending on whether we are using pegged or unpegged, as for me, I have chosen the pegged method, would be 4-bit or 8-bit. Using my pegged method or the 4-bit register, this register will use 0, 0, 0, 0. That register will be 0, 1, 0, 0, and this register will be 1, 0, 0, 0. This is the BCD representation of that number over there, or that time over there. Okay. In some situations, you may be presented a problem like this. Okay, here is the BCD. Here is the register. Okay, these are the 3 registers, and inside the 3 registers we have inside the 3 registers we have 1, 0, 0, 1. We have 0, 1, 1, 0, and 0, 0, 1, 1. If the top register is holding 840, what is this bottom register? What is this bottom format holding? You go back to your binary to decimal conversions. 1001, this is 9. And if we look at the notation at the top, we follow with 2 dots. And after that one, we have 4 plus 2, this is 6. And the last one is 3. So if this one was holding 840, then the bottom one is holding 963. I have never seen a time like that. I did not check before I gave that example, but that's pretty much how BCD works. Alright, so converting from the displayed number to the contents of each register is very easy, but adding what is in BCD format might be a little challenging. So let's get to look at that. All right. So I'm going to use the addition of, let's say this is money. So I'm going to put $sign here. Let's say I have $4.28, and I also have $7.44. If I add this money, it must add up to 8 plus 4, that's 11, no, that's 12, carry 1, that one is 7, this one is 11. So you would see that if I am to have 428 in BCD and 744 in BCD, my solution requires 4 registers. One register to hold this digit, the other register to hold that digit, and that digit. But let me just add my binaries straight away from the registers. I'll put the register for the $sign and the comma, I ignore them. I'm making space for 428. 1, 2, 3, 4. 1, 2, 3, 4. 2, 3, 4 bit registers. So 4 is going to be 0, 1, 0, 0. 2 is going to be 0, 0, 1, 0. And 8 is going to be 1, 0, 0, 0. Then 744 is going to come into this register. Put a comma there. One, two, three, four. 1, 2, 3, 4. 1, 2, 3, 4. All right. Now my 7 is going to be, I know there's a 1 here. I know there should be a 1 here and a 1 here. Then 0, 0, 1, 1, 1. That is 4 plus 2, 6 plus 1, yes. Then 44 is going to be 0, 1, 0, 0, 0, 1, 0, 0. Okay, that was just not very important. Now let's add 428 in BCD notation and 744 in BCD notation. If you add the old way of adding binary numbers, where 1 plus 0 is equal to 1, 1 plus 1 is equal to 0, carry 1. Let's see how it will end up. So from the least significant nibble, we have 0 plus 0. We get a 0. Let me also do this. Let me put the registers for the answer. Okay, so these are the registers which are supposed to hold the answer. And let me even put more space here because we have already seen that we are going to need 4 registers for our answer. So let me add, just in case we have an overflow and we want to move the other bit to the 4th register. Okay, so back to 0 plus 0. I'm looking at this row now. We get 0, 0 plus 0, we get 0, 0 plus 1, we get 1, 1 plus 0, we get 1. 0 plus 0, I'm now on the 2nd register row. We get 0 here. 1 plus 0, we get 0. 0 plus 1, we get 1. 0 plus 0, we get 0. Okay. 0 plus 1, we get 1. 0 plus 1, we get 1. 1 plus 1, we get 0, carry 1. 1 plus 0, 0, we get 1, like that. So we did not get a carry to put here. Let's now decode our value, which would be displayed. Let's say this is a cashier's calculator which is working here. The first nibble, or let the rightmost nibble with this one which I am circling in green. What is the value there? 11008 plus 4, that is 12. This is a problem. We have a calculator which has a space for 1 digit, but the register is a value 12. 12 is 1 and 2. These are 2 digits. They cannot fit on the display of the calculator, so there is a problem here. All right, let's go to the next one. Then we have a comma here. 0100, that is 4. This one is fine. 1011, this is space for 1 digit, but we have 8, 9, 10, 11. We have 11 here. The display is space for 1 digit, but our register is giving us a 2-digit value. That is a problem. So that's an error. Those are the 2 errors which we are getting from trying to use the good old binary addition to BCD. Now, whenever a CPU detects an error like that, a CPU should actually be able to detect an error like that. When it detects that error, it must provide a remedy so that the calculation becomes correct. How is that remedy going to happen? Whenever a CPU detects an overflow like that, okay, let me not call it an overflow, an error like that, it must add 0110. Whenever it encounters that mistake, it must add 0110. So let's do away with this whole thing. We saw that, okay, it's a little messed up. So let's start again and do it the right way. The previous way was a wrong way. This is the right way which you must use. Avoid the previous way, use this way. Okay, we want to get to 1172. Oh, sorry, let me do some comparisons here. Okay, we wanted to get to 1172 like this one. This is the correct answer, but we got 11,412. There are two problems. This is just wrong, and the other problem is we are having two digits in place of one, in a place where the display can only display one digit. So those are the problems we have to remedy with the CPU. Has to remedy whenever it encounters errors like that. So let's start again, now taking note of the need to correct the errors whenever they arise. We've already seen that there's a problem here, so we start with that one. 0 plus 0 is 0, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 1. Adding this one, this is 12. There is an error already because our display can only display from 0 to 9. So we must add 1, 2, 3, 4. We must add that remedy, which is 0, 1, 1, 0. We must add it to this, and what do we get? Alright, now we got this value and we are adding this remedy so that we can correct the problem. 0 plus 0. Alright, sorry, I did not change that. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0, remainder 1, 1 plus 1 plus 0, that is 0, carry 1. So we are carrying this 1. This register is now holding a 2, 0, 0, 1, 0 is 2. And that 2 can fit on our display because it's a single digit. This carried over number, this 1, we now bring it to the second display. We now bring it to the second display. Now, on the second display, let me take the carried number and put it in green. So this is the carried number here in green. And let me delete it at the bottom so that it becomes a little neat. Alright, let's add the value to be displayed on the second slot. We have the green value, which is a 1 there. Oh, sorry, 1, 2, 3. The green value, which is a 1 plus 0 plus 0, we get a 1. 1 plus 0, we get a 1. 0 plus 1, we get a 1. 0 plus 0, we get a 0. 0, 1, 1, 1 is 4 plus 2 plus 1, that is 7. So if it is a 7, it means it's a good number, it can fit. There is no need for a remedy here. So we just bring it down as it is. 0, 1, 1, 1. Okay, so that digit was fine. Let's go to the last digits here. Let's add them and see what they give us. 0 plus 1, we did not carry over anything from the middle number there. Just before the comma, we did not carry over anything, so we start afresh there. 0 plus 1, we have 1. 0 plus 1, we have 1. 1 plus 1, we have 0, carry 1. We carry that 1. 1 plus 0, we have 1. This number is 1011. If we convert it to decimal, it's 11. 11 is going to be displayed on a display that is capable of displaying one digit. So there is an error. We need to remedy that. We remedy it by adding 0110. 0110. Okay, so if we add 0110 to the contents here, we would have solved the problem for this particular register and its display. So 1 plus 0, okay, sorry, 1 plus 0, it's 1. 1 plus 1, 0, carry 1. 1 plus 0 plus 1, it's 0, carry 1. 1 plus 1 plus 0, it's 0, carry 1. So this register is 0001, and you have a 1 carry to the next. 1 carry to the next would require another register. And since this was more like 00, there is nothing here more than 000. This 1 carried over, let me put it in green here and delete it from this point. That one in green plus 0, we get a 1, and everything would give us 000. So now, decoding the numbers from either side, I'll start from the least significant nibble. 00, I'm talking about this part now. 0010 is 2. 0111 is 7. Then we have a comma here. 0001 is 1. 0001 is 1 again. Now we have our solution 1172, which is the solution that we got when we calculated our values in decimal without converting them to BCD. So the take from all this trouble is when you are adding the binary numbers in BCD, you have to be very careful with the value which is in each register. Whenever a value in a register goes beyond 9, you must correct that problem by adding a carry bit or a carry nibble, so that you don't get a number that has 2 digits in a single register. It doesn't matter whether you are using 8-bit or 4-bit. Remember, with the 8-bit, the first 4 zeros are dummy values. They don't have to change to anything else. They must stay zeros. So you always get your values in the PECD format, which uses the 4 bits. All right. I don't think I will give another examples for this one, simply because of the trouble which it takes us through. I don't want to make a video which is too long. So bye bye for now. Let's